Good afternoon, everyone. Welcome to this CQSE seminar. We are happy to have Professor Shih-Hao to give us a talk. Professor Hong graduated from National Taiwan University with a bachelor degree in electrical engineering in 1989, and he then went to University of Michigan for his master and PhD degree, and then he received his PhD degree in 1998, and he then completed the postdoc, also worked as a postdoc also at the University of Michigan from 1998 to 2000, and then in 2000 he worked at Sun Microsystem in California from 2000 to 2005, and then he joined the Department of Computer Science and Information Engineering in National Taiwan University in 2005, and he currently serves as a department chair and also serves as a Deputy Director General at the National Center for High Performance Computing. He will talk about the trend in high performance computing today. Let's welcome him.
Thank you for the introduction. I'm afraid that my English is not good enough, so do I have to talk in English? Yes. Then you have to accept my poor English. Okay. Okay. All right. So I'm going to share my view of the trends in high performance computing. This is my favorite topic to talk about, since my PhD thesis is also about high performance computing. I was excited when I had the chance to play with supercomputers when I went to study in Michigan. That's a rare opportunity. But today, almost everybody around here has a chance to play with supercomputers, as long as you pay a little bit money, or with your research project, you can use the supercomputer service at the NCTS-CASTS-CTP National Center for High Performance Computing. Okay. In the old days, we used to do these applications. The users are people like you from physics department, from engineering departments, but rarely from computer science, because computer science like to play with data. But today, the story changes. People used to run scientific and engineering applications, something like nuclear simulation, something like climate simulation, on supercomputers, but today it's also changing. Software used to be simple, just some parallel software. You have to write your program in parallel language, such as MPI or OpenMP, etc. And it runs on specialized FT hardware. They are also expensive in old days. But today it's different. Today we have lots of industry and business users. They want high performance computing to shorten the execution time. They want the answer immediately. For example, big data and AI. They have lots of data but want to get the data analyzed in short time, say minutes or even seconds. The AI wants to be better than the other people's AI, so they use HPC to do it, or they have lots of data to train the AI. They want to do it in, say, hours instead of weeks. So they spend a lot of money in software and hardware. Hardware is interesting. I'm going to talk about perhaps a little bit about quantum, because I'm in here. And I know some of you are very into quantum computing. So I will cover a little bit about this new HPC hardware. The way you use quantum, or the idea to use quantum computing, is to speed up the execution. You want to achieve so-called quantum supremacy, to be like thousands or tens of thousands of speed up over the traditional high-performance computing. But today we have something like GPU or deep learning accelerators or something else to speed up anything that you want to get the answer in short time. Okay, so this is changing from traditional to today's. The short summary is that today's HPC are diversified and specialized. So if you have an application, you better find suitable hardware or suitable system to run it. The efficiency and performance will be much better that way. This is challenges and opportunities. For example, if you want to do high-performance deep learning, you have some choices. For example, it depends on your application. Is running on data center, in the cloud, or running on edge devices such as your cell phone. That's different kind of applications. And you have your choice of neural architecture. It can be simple neural network or very complicated neural network. But sometimes the key is to collect data. Data privacy is also a big issue today. Where are the data come from? They come from your own company or they come from everywhere. Of course, ideally it's coming from everyone and collected to the cloud so we can do centralized analysis to get the best use of these data. But in practice, it's not that easy because we have privacy to take care of. So sometimes people resort to federated learning. So you can do analysis independently in each location and summarize the results to get better machine learning models, but at some sort of performance and cost trade-offs. And on the bottom, you have different kinds of accelerators. So when I was at the conference yesterday, I was also facing some HPC users. I say, let's work together, and because in today's situation, if we don't work together, you will not get the best out of HPC, and your application will be not so advanced. So collaboration is key, and I also want to send a message to you guys if you want to work on HPC or any very hard problem that can solve with high-performance computing. You can come to me or come to HSC. We can try to work with you to get answer because today's systems are very complicated. It's hard to harness this complicated system. You probably have to take computer architecture lessons to gain some understanding about this processor architecture. And also you have to pay attention to something like multi-core or the connections between many machines. These are, for you, maybe very tedious. So you probably need our help. Consider us like toolmen. You can go to you can use us to solve your problems. Applications, for example, this is last year's #1 supercomputer from the National Lab in Oak Ridge National Lab in the United States. Their supercomputer runs so-called mission-critical workflows combined with model simulation, AI, and big data analytics. And they want more computing power, more and more. So I guess next year we will see really exascale computers. It's capable of executing 1 exa floating-point operations per second. That's called exascale. It's coming next year. So it shows us how important supercomputer is to the US and also to other big countries. But I think it matters to Taiwan too, because the applications is a lot. And this is for quantum computing. they are looking at these application areas because quantum computer has so far has some narrow application areas, much narrower than traditional computer. So you have to pay attention to the application areas. These are probably some of the application areas that show some results with quantum computers. I will cover it a little bit in my later slides. About the hardware, we are facing this situation. Today is already past 2020. We still see the growth in transistors per area. The density of transistors is still going, thanks to companies such as TSMC. So it gave us this so-called MOSFET. So we computer architects use MOSFET created the transistors to build our processors, but we can not afford to put all the transistors into one processor cores because that would be a very big but very inefficient core. So since 2005, the extra transistors are used to build many cores. So the number of cores are growing. So today, your computers are almost always many cores, something like 4, 8, even 32, or even 128 cores, and sometimes more if you have GPUs. And today we hit the so-called power wall here. The power stay at something like 150 or 200. If you push a little bit, you can get a processor that's very hot, working at 300 watts. But we could not push more unless you have a very exotic cooling device to cool the processor chip down. But that would be a little bit expensive. For everyday system, it's fixed at, say, 200 watts. So that limits our operating frequency. So your processor are not getting faster if you use single core because of this power wall. So what do? You have to write payload programs if you want to get your program run faster on today's processors. Because more cores with better efficiency, you can achieve more jobs done this way. So we see some trends for today and post-war era. For example, many chips, because each chip has roughly 200 watts, and we do not want to cool down more power on this small area. So the way to do it is to separate it into separate chips. And the other thinking is that the bigger your chip is, it's easier to get defects during the manufacturing process. So you have to throw out the chip. It's called yield rate. So you want to control the size of one chip. So if you want high performance, you have to use many chips. Like here, we have 8 chips and connect it with the best, the fattest interconnection network you can get from the market. So this is a machine built by NVIDIA in 2019, and it's also the building block of today's many of supercomputers in the last 2 years, using this as a basic building blocks and connect many of these machines with networks. Last year, they have this new chip and new system. They improve the connections. So these chips, unlike previous version has point-to-point connections. So when this GPU wants to communicate with the GPU on the other side, it has to go through a few distances, a few links. That takes time. But today, the newer generation of the system has a powerful switch, so every GPU can quickly talk to each other in this new architecture. Okay. So it's improving, and computing power mainly come from the GPUs, not the CPU. I did not talk about the CPU in these two pictures because they are kind of boring. Okay. The latest technologies are in the GPU. It has how many GPU cores? Many. If you multiply by 128 by some numbers, you will see like more than tens of thousands cores in this chip. A lot of computing power, but you have to write program in a different way, not the traditional OpenMP, not traditional C or Fortran. You have to learn some new languages. Fortunately, it's not that difficult. If you want to take some lessons, you can help. You can harness this monster. So it gets to 8,000. This is a smaller version. If you have the full version, it will be bigger. For the sake of time, I will skip some of the boring slide for you. This slide shows the internal architecture. One thing to pay attention is that they have some special weapon. This so-called tensor core is not like traditional 14-point operation units. It is intended to process so-called tensor. Also, you can call it matrix or vectors. Tensor is, I guess, more general. You can have multi-dimension vectors and send them to this tensor core to get 10 times of processing speed. So this is the way in modern processor chip to improve this efficiency in processing data. The principle is like you send the data into this tensor core. It doesn't have to store the result after one instruction. You can continue to process in this tensor core to save some trips to the memory. And also you have to pay attention to the data types. So we used to have these 40-point 32-bit, that's standard. So if you write program, you declare a variable which is float. That's automatically 40.32. But today sometimes we have to save the execution time by trimming the data types. For example, this TF32, it's not really 40.32. It has a small, less precision because this areas is shrunk from 32 bits to 10 bits. So the precision reduced, but this is very useful if you want to do so-called approximate computing. For example, your neural network in your brain, it doesn't always do precise computation. It can tolerate some errors or imprecision. Our artificial neural network is also like that, so they can take advantage of this new data type, or even like brain for boiling point 16 is even shorter and more efficient data type to do deep learning applications. And also the latest hardware support so-called sparse operations, because they find many of maybe your problem also have some sparsity. Say that your matrix has some areas that's very close to zero, and sometimes you can just trim them into zero, so you have a data structure, a matrix that's maybe half of them are zero entries. And the hardware will compress this matrix and have the tensor core does useful computation on those non-zero data values that could improve up to 2 times speed up. Okay, you can see we had to try every tricks, try to squeeze the performance in the latest computer architecture. And it's very, as I said, it's very power hungry. For example, this system, 8 GPUs, it consumes 6,500 watts. It's very hot and it's also very heavy. This thing weighs like more than 100 kilowatts. It's like 2 humans, but in a small box. This is top 100. As I said, there are several supercomputers scheduled to exceed exascale. This year, later this year, we will see Orion Frontier that's start to work at 1 exaflops and also 1.5 exaflops. Next year we'll have El Capitan. Not we, the US will have El Capitan running at 2 exascales. Okay. I'll skip some of these slides. Supercomputer or high performance computing is not only on the computing side. The more important thing is you have to feed data quickly enough into these processors to keep them busy. Okay. So the capability to do network and I/O is become a very important issue in today's high-performance computer. For example, you want to connect 140 nodes. The computer I just showed, the DGX A100. How do you do that? You have to use a lot of switches to do it. This is from NVIDIA's reference architecture. And these are at least gigabit or even 200 gigabit per second networks per link. So that you can have these nodes communicate at very high data speed. And also storage, you have to feed the data into these computing node quick enough. So the storage has to have a separate but also reliable high performance link to these computing nodes. As I said, these machines are power hungry and heavy. So although these chassis can hold, can still have some space, but you cannot put them fully in these chassis because power and the weight constraint. Some of the floors, high-rise floors in the data center will not hold if you have too many machines. These heavyweight machines in a chassis. But this is an interesting problem in our data center. Yesterday, we invited some guests to see our latest supercomputer. It's called Taiwanese 3, Taiwan Shih-Hao. This is a very annoying problem, noise. It's very noisy because these the fans in these machines are rotating like crazy and generating a very high noise. Even the staff can hear the noise on the second floor, and they know how these machines are working correctly, or some programmer just had some program died because the machine would went from very noisy to quiet, so they know that some program has crashed. In Google, they have special weapon. This specialized chip is called the TPU, Tensor Processing Unit. As you can see here, they do not use air cool, they use liquid cooling device. There's 4 TPU chips on one motherboard. But this is not for sale. They do not want to sell it to other companies because they they have lots of these in Google's data center to do service for us. So when you speak something, you want Google to translate it into text or translate from one language to another. They use TPU to do these translations at very high efficiency. Later, I will show you from the news next month. Google started to use TPU to accelerate quantum computing programs. That's an interesting development. I will show you a little bit how they do it. And this was from 2 years ago. They started a new development with this so-called wafer scale engine. This is a wafer. Wafer usually is a round thing, but they only keep this square. But this is a big square area. The largest GPU at that time is big, and this big already, say, 350 watts. This whole wafer has so many transistors and so many AI cores, so many memories. And these AI cores can connect to each other from left to right, from upper up to bottom at very high speed. So the idea is simple. If you want to build a supercomputer, why do you have to cut these into separate chips and connect them with network? Why don't you just implement the network on this wafer to make it a supercomputer? So, of course, it has some challenges, but TSMC has done it, has overcome some challenges to make this practical. And actually, there's a Gen 2, so it's not just one shot. In last year, they have Generation 2 wafer scale engine. It took advantage of TSMC's 7 nanometer technology. The transistor count improved from, say here, 1.2 trillion to 6.6 trillion. So it's very amazing. And also other new emerging HPC architectures. But you can see they are kind of specialized. This guy is specialized for AI operations. This guy is specialized for graph. As the name suggests, it's graph core for graph processing. Of course, if we want to get more, post more, we may have to resort to quantum computer to keep the morsel alive. We are here, 2031. Whether we can keep it going, it's a very interesting question. But we already showed some promising, see some promising results from some of these companies. They claim to achieve quantum supremacy, for example. Google said it did it. IBM said, no, you don't. So there's some debate about whether this is true or not. But it's also exciting to see these debates between big companies. So I will cover quantum computing in a little bit. But I want to mention a very important issue that we face in practice. That's a data privacy issue. It has been stopping people from taking advantage of big data and do AI. So I think we are investigating some effort on so-called privacy-enhancing technologies. And for example, as I just mentioned, we don't have to send the data out if we can do it locally. Or if I want some analysis done, I don't have to get the data, I just send the program to you and you can run the program with your data and send me the result back. Okay, this is the idea of federated learning. But it also has some issues. Maybe I'll talk about when we have time in the next talk. I don't know when will that happen. And this is also an area that has some history. Actually, 30 years ago, people already talk about doing computation in the encrypted domain, so-called encrypted computation. I sent you a few numbers, encrypted, so you don't know these numbers are. But I have you do some operations and send the result back to me. I can know what the result, and I know what's the meaning of the result. So who did the computation doesn't know the original data and even doesn't know the result. So we can avoid the data leak happens. And there are two kinds of algorithms to do this encrypted computation. For example, we can have many people work on the same operation, but everyone just do a little bit of the computation. So each person doesn't really know the big picture. Only who handles the whole operation understand what each individual are doing and the overall result. It can be done, but at the cost of very high communication overhead. So if I want to do it here, I can do it. I want to do the additional two numbers. For example, 1, 2, 3 plus 4, 5, 6. I can divide these two numbers into, say, 100 pieces and send it to 100 guys here. And everyone do a small computation, but you don't know the original number, only the result makes sense to me. But the communication overhead is very huge because I have to send the divided number into to everyone and collect the result back. The other type is so-called homomorphic encryption. That's even more expensive at the computation. The idea is to transform the numbers into a different domain and with different operations, but the operations can be converted back to the original domain to get the results. So I can have you do the computation in a different domain, so you don't really know what the data means in the original domain, but only I can decrypt the results. It takes time, but the time is shortened with today's technology. It used to be overhead that's too large to be practical, but today we can do encrypted computation in milliseconds. So that makes sense in the industry. So industry has begun to pay attention to homomorphic encryption. For example, this is a project being executed in Facebook. They have this open source project called QuickTime. But basically, companies like Facebook has been challenged with privacy protection issues. Basically, they are charged for abusing data provided by the users, etc. So they are paying attention to this kind of technology. For example, some of the data after encryption, so those who does inference or even training doesn't really know the original data, or they don't get to see what the machine learning model is, but they can do the computation. This happens, say, in the data center. The other way around is also possible. I can give you a model to run on your computer, but the model is encrypted, so you don't know what, you cannot steal my model, you cannot steal my intellectual property, but you can get the results. And there are some issues still worth research today. So finally, I think we have to talk a little bit about quantum computer. Otherwise, some of you may be disappointed. It's a completely different programming model. So I have to admit I do not know how to write the program, but my students can, so I have to write it. It takes a different type of programming paradigm. Basically, you have to connect the qubits with some sort of operations and assemble it into some kind of circuits to do it. And qubits makes no sense to electrical or computer science engineers, because for computer science, each bit is either 0 or 1, but for qubit, it can be something between 0 and 1 and with some kind of probability. So this is completely different data structure and different programming model. So if you are good at it, you may be able to achieve quantum supremacy. Unlike, we just say the Moore's law, with more transistors, we can do more computation. That's one-to-one relation. But for quantum, with more qubits, you get exponential problem-solving power. So the companies are trying hard to increase the number of qubits. That's another problem. The quantum computers are hard to build right. How to build right. If you build a quantum computer, you have to pay attention to the error rate to keep the status low enough to finish the computation. Sometimes you have to keep the quantum computer in ultra cold so they can last longer, and it's expensive to do that. So I don't know when people will solve that problem, but many companies are trying hard to solve this problem. Unlike we have very mature technologies to build traditional computers with semiconductor technologies and design the chips. And today, some optimization problems or financial analysis or some simulations can be done pretty well with quantum computer. But compared to today's computer applications, they are only very small, very tiny areas. And this is also challenges and opportunities. Last year, Fujitsu trying to sell us their quantum computing solutions. Fujitsu is here. They said that they have been developing so-called digital annealer since 2018. We didn't buy it. It's too expensive. And we say, okay, you can give us, you can sell us a small one and put it in NCHC. They say no. They are afraid that we will be able to copy it, to reverse engineer it and copy it. Because this guy is built with purely digital technologies, that is semiconductor chips and ICs. So we maybe really, if we get a machine like this, we can disassemble it and try to reverse engineer it. That's a very valid concern, so they will not ship it to us. They say you can rent it, but the rental fee is too high. So at the end, they just say we can give you some free execution time to try it out. So we actually tried this Fujitsu digital annealer. To some people, this is not true quantum computer. You can call it quantum-inspired computer because it operates with some principles that's borrowed from quantum computer. The true quantum computers are on the right-hand side. For example, IBM-Q, many of you are aware of because we, NTU, are signed with a contract with IBM. We can have access to IBM-Q here. Also, Google and other companies are trying to build this so-called quantum gate systems. It runs programs with written as quantum circuits with different gates in this circuit, so they are called quantum gate system. The thing is, there are several hybrids. For example, quantum annealer. Try to do the simulated annealing algorithm with quantum hardware to do it. So you can see they use superconducting circuit trying to do this with qubits and annealing algorithms. And this is why they call it quantum-inspired solutions, because these things are also doing annealing with ideas borrowed from quantum annealer. I can say a little bit about digital annealer because we are trying to build digital annealers by ourselves. They are not that difficult. You can even use existing systems to do digital annealing, just writing programs. The answer is yes, we can do it. These are from my students. They surveyed some papers, especially papers published by some Japanese companies. For example, Fujitsu is one of them, Toshiba, and the others. I keep forgetting their names. Like here, AEC, here, Hitachi, and Toshiba. These Japanese companies, they like annealers, so they devote quite a few efforts and write some papers on annealer. So we just survey the papers to show that we can do it. So we select a few of them and try this experiment. For example, we take SB and run it on GPU. We take this algorithm called SCA and run it on GPU. We also took SCA and run it on, took this SQA and run it on FPGA and GPU to show the feasibility. These algorithms are intended to solve this so-called IC model. If you can transform your problem into an IC model, then you have a chance to solve your problem with these one of these solutions. Okay. Would this be the best? It's hard to say. You have to look at the result. Here I will say a little bit about annealing. So this paper shows how they borrow ideas from quantum computing and put it into digital annealing. So originally, people are doing so-called simulated annealing, but they added the idea from quantum computer and say that the annealing can be done exponentially faster by this improved algorithm. So this is traditional simulated annealing. We borrowed from annealing physics, but basically it's a Monte Carlo Markov chain algorithm. Continues to run a loop, and by reducing the temperature, and eventually you will get the optimized solution, hopefully. And quantum dynamics is behind this reality. You do the annealing process in the physical world. Quantum dynamics is behind it. But if you do simulated annealing, it doesn't really include the quantum dynamics. So the author of this paper here, Elizabeth, it says, okay, let's add quantum dynamics into SA. Quantum dynamics, what she refers to is this tunneling effect. When we try to solve optimization problem, we almost always have to face this barrier you find local minima here, but you are trapped. In fact, the global minima is here, but you cannot get through this because there's barrier. The barrier is too high. When you do a search, you can only this way. But in the world of quantum dynamics, it has a chance, probability to tunnel through this barrier. But we can simulate this quantum dynamics effect in our program. So that's what they did in that paper. Then in 2019, this Toho University is in Japan. It works with, I forgot which company, but it doesn't matter. They implement that quantum annealing solution simulation with hardware acceleration. You use FPGA and write the OpenCL program to do it. So the idea is that this is the original domain. It's two-dimensional, as shown in this picture. To simulate the quantum dynamics, we create an extra dimension. They call it trotter. So it becomes three-dimensional, but actually the original problem is two-dimensional. The extra dimension gives the capability to tunnel through some high barriers. Okay. So this is computer science way to achieve quantum tunneling effect. And it has some speed up. Show the code to show you that you can also do it. You just read the paper and implement the code. It's not that difficult. Our student did it. He did it in, I think, a couple of weeks. And this is the result from Tohoku University. They use CPU and GPU, FPGA. FPGA is faster, so you can see speed up from 7 to 12. We also did it with FPGA and get a comparable result, and sometimes even faster because our board is newer and with faster memory. So some of the results we did, for example, here, are better than theirs. So we first show that we can reproduce the work of SQA. Then we try to reproduce the other work. Is SQA running on a GPU, a GPU-based quantum annealing simulator. It's also from Toho. The code is about the same. It has to be rewritten for the GPU with some different structures. But basically, it's the same algorithm. And GPU has the advantage of solving bigger problems. Although the execution time is longer, the bottom line is from FPGA, but it stops here. These dotted lines cannot be implemented with current FPGA implementation, so it's estimated. But with today's GPU systems, you can easily scale the performance to solve bigger problems. That's the advantage of GPU. It's ready to acquire components, and there are many supercomputers with many GPUs on the systems, so you can easily use GPU to solve large problems. We also port the GPU core onto our systems and got some result that's comparable. And next is so-called simulated bifurcation. This is work from Toshiba. It's another quantum dynamics ideas. So they compare SB versus the other works. SA is the original simulated annealing. So they typically show a picture like this to show its advantage. This shows us SB is capable of finding better solutions here with shorter time. The x-axis is the computation time. This is better than here. And the energy, lower energy is better. So this is the best result they can find with 0.1 milliseconds. It takes longer for the other method to find. In terms of performance, this is probably 100 times better than traditional SA. And here shows the solution quality. SA is not deterministic algorithm. It's probability. It has to do with probability. Sometimes you can only hope it get the best solution, but sometimes it's more or less. Skip this. I only have 5 minutes left, so let me speed up. Okay. In 2020, there is a paper published in this conference, ISSCC. It introduced the idea of SCA, stochastic cellular automata. Again, it's intended to solve combinational optimization problem with annealing algorithms by adding ideas from quantum. So again, this is the formulation of Ising model. They just transform this equation into another equivalent equation, but this formation can be done with parallel computing instead of solving steps one by one, one after another. It is capable of solving the steps in parallel. That's why it gets better performance. That's the result. SCA, again, is much faster. They claim it's 2,000 times faster than traditional SCA algorithm. So we see a lot of annealing works in the recent years. Every time a new technology, a new paper shows up, it claims the best of the world. Okay. And we can reproduce this effort. Our implementation on CPU, on GPU, is 10 times slower, but it shows that we understand how this algorithm works and in practice, and we can try to port it to hardware if we are given a chance. Finally, I want to mention this work. It's not long ago we received this news. Alphabet is the parent company of Google. So they, of course, have access to Google's TPU, the specialized chip for deep learning. They use TPU for quantum computing simulations. How did they do that? Unique hardware, of course. This is not for sale. They have this tensor processing unit, and they have a lot of them. So they just convert quantum computing software or programs to run on this TPU and to take advantage of the computing power. And results, I think when I read the report, it says something around 1,000 times faster than GPU. But I suppose the GPU they refer to are not fully optimized, the GPU, because as I mentioned in the talk, GPU has tensor core, and some of my students are using the tensor cores in the GPU to do quantum computer simulations or to do the digital annealing. So these are the same directions, but I guess Google has this very specialized chip. They have this advantage to do it with some very interesting result, but it's not really disclosed yet. So we are waiting to see the published result. Finally, to conclude, I think HPC is more important than ever. Although quantum computer is on the verge, but it's not really ready yet. To use today's supercomputer is very important. It's very important. There are already many applications, and quantum computing, the development of quantum computing can also depend on supercomputers, because you have to validate your quantum computer programs or to simulate your quantum computers. Then it can be a job for these supercomputers. Eric Smith, he used to be the president of Google. He warned the U.S. government Silicon Valley could lose to China if they are not prepared. That's why the United States are paying attention today to supercomputers. In Taiwan, I think we have a chance. As I said, in NCHC, we have some medium-sized supercomputers that can be used by the industry, also the academia, to do high-performance computing. And Taiwan has also Taiwan also has many very good hardware engineers. And Taiwan also has TSMC to make the chip, that state-of-the-art chip. So it has a chance. Our country has a chance to shine in HPC or even in the quantum computing era. Okay, so that's the end of my talk. Thank you for listening.
All right, questions?
Thanks for a nice talk. You have shown that wafer scale engine.
Yes.
And you show a big chip, and in my image that the chip has all the chip used now only small and much bigger fan on the chip to cool down that chip. But you showed such a big chip. I'm curious how to cool down this.
Okay. Yeah, that's an interesting question. I used to have a slide following this. That they have, it's like a refrigerator. The whole machine is like a refrigerator, but there is only chip inside the refrigerator.
Wow.
So they use a big device to cool down this wafer, and I think they have to use state-of-the-art cooling technologies to do it, so it's not cheap.
So it use this chip to maybe say build a computer, it may be a much bigger one and only this single chip inside that computer. Or it can put many chips together to build like a work center.
It depends on the cooling. It doesn't solve the problem of power wall. So you still have to cool it down. For example, I don't have the number here, but the power dissipation is, the heat dissipation is a very big number, so you have to try to cool it down. And even you have more of these, you cannot stack them together because there's no way to cool down this kind of chip. So actually the power is still a concern, but this solves an important problem, that's the interprocessor communication problem, because as you can see here, you have to have a switch to connect these things and the switch to connect these things. And these are also power-hungry chips. And to send the data in high speed between processors, it also needs additional power to do the transmission. So these are very significant overhead. By putting all these devices in one wafer, it shortens the distance and saves the power to do these communications.
So the switch is also fabricated on that chip?
It's on the wafer, on the wafer engine. And here, let me show the picture. These are the heatsink for the A100. That's why it's so heavy. And on the other side, there's also heatsinks for the switch because it's also power hungry.
I see. So, can I image that so-called wafer scale engine you have built most of the function onto that wafer?
Yes.
So,
yeah, so, but you can see it's homogeneous, meaning that every chip is the same. It's just a massively parallel computer. There are interconnections, and also memory is already in here, so it doesn't have separate memory modules. Unlike our computers, you have CPU and memory and the other things.
Not every function on different part, but every every block has some.
Every block is a. You can regard every block is a small computer, and it has its own memory here. This is already 3D, so usually 3D chip has logic, processing logic on top, and memory on the bottom, so they can have vertical ways to access data faster. So each one is you can see each one is probably something like this, and there is interconnection between each small components. And if you look at this number, 100 petabits, that's insane, because our network are gigabits, and terabits, and petabits. So this shows the purpose of building such a big wafer scale chip.
Thank you.
So thank you very much. That was very interesting. And I wanted to ask, I'll just speak up. I wanted to ask, so there's all the, like you mentioned, a lot of these very specialized architectures, like the Google's TPU, and some of these other things they're using to build these like top 500 supercomputing. But there's a certain extent to which I think, like, well, if you're Google and you know exactly what very specific problem you want to solve, it makes sense to build this specialized hardware.
Yeah.
And if you are Lawrence Livermore National Lab and you want to realistically probably run simulations on whether or not the hydrogen bombs still work, like then you have the same thing, a very specific problem, and you can build this specialized hardware, and But then I sort of think like, oh, for like scientific computing, or if you're a smaller company, you don't necessarily, you don't have the, like it seems like these are not going to necessarily be very helpful to, unless you really know this very specific application that you have. Like, is that
Yes.
it?
Yeah. So one way is to try to explore the possibility of using, for example, some chips that's designed for example here, designed for AI deep learning workloads. But if you have access to this type of machine and your workload can be somehow converted to run on this chip, then it's great. For example, here is another thing for AI acceleration, and first you have to have volumes to be able to be produced on the latest technology. Here, 3 nanometer. 3 nanometer is considered an expensive technology, and if you only order, say, 1,000 chips, it's not possible. It has to have volume or value to be able to be produced with the latest semiconductor technology. And that's the reality. So we can take along, so you can observe some of the new ongoing projects and new emerging products, and try to think of a way to convert your simulation or your applications to fit here. Maybe part of them can fit here, and the other part still runs on CPU or GPU, and to get the best out of this technology. That's my view. So, for example, the TPU was designed for AI, but somehow Google used it to support quantum computers. So that's an example.
One question, one comment. Okay, I take and make a fast calculation for this chip. Is 21.5 centimeter times 21.5 centimeter. So it actually fit in one wafer. Right? Actually fit in one wafer. I think 8-inch probably is okay, or 12-inch, of course. Right? So this is actually the second, at least the second try, in computing history.
Here, there's a dimension, I think.
Yeah. That's equal to 21.5 centimeter times 21.5 centimeter. It's about this big. Yeah,
yes.
It's about this big. So, back in 1980s, AMDO tried to do a wafer scale integration for a computer. Back in 1980s, so it fails. Yeah. And my second guess is that this thing, I think it also contains some redundant circuitry.
Sure.
Yeah. Otherwise, I just cannot believe that, every transistor, they got the 100% yield rate in all the transistor, 1.2 trillion transistors in this chip. I just cannot believe it. So there's a redundant circuit too, right?
Yeah.
Yeah.
So you're right.
Yeah.
It's hard to do it perfectly. So they must contain lots of defects. Unfortunately, they pick an easy application to deal with the defects, because this is intended for deep learning in AI, and it can tolerate those errors. So it's easier to solve than the other kinds of applications. So if you want to do financial computing, you probably don't want to mess with it here.
My question is, you have slides talking about the sparse metric.
Yes.
Yeah. I just wonder that in this architecture, do they use a systolic array for
Yes.
the hardware implementation?
Yeah, systolic array is here. So this implies a systolic array, but not strictly speaking the original systolic array, but it's a similar structure. Basically, after you compress, they just put a compressed engine in front of this
Accumulate.
tensor core, so make it sparse tensor core. But after compression is dense, and they send the dense data into this systolic array like processor engine to do these dot products. And repeatedly, the dot products would produce the results of matrix computation.
Any other questions? If not, we still have the tea after the talk, so you can stay, and I hope Professor have some time, then you can still chat a little bit. Okay, thank you.
Okay. Thank you.